Tonight we're going to take a look at the Is This a Binary Tree challenge from Topcoder. Now what I've done is I've coded a very simple binary tree. There's not a lot going on here. Binary search tree. Not a lot going on here. I've basically just created a node and I build my tree off of that node. There's no real need to create a separate binary search tree class for this. Using my node, I included the enumerables module. I create an adder accessor for data left and right. Data is just the numerical data that we're going to be passing in. Left and right are both set to nil initially for the node. Okay, then I overwrite the each block, and this is just to traverse the node down the length of the tree, and then yield the data from that. What I'm doing with this each block is I'm using this each block to test to make sure that the items are valid. Now I'm using the each cons method to test the consecutive two, so each consecutive two items in the array of all of the items that are going to come in. Remember, this is the data from the each block here. It's going to see if A is less than B. If A is less than B, then we have a valid binary search tree. Then, because the parameters for this challenge request that a binary search tree be working both in the known method of the numbers that are smaller than the root to the left of the root, the numbers that are larger than the node be to the right of the node. This asks that a valid binary search tree could be reversed, in which the numbers greater than the node would be to the left and smaller than the node would be to the right. So I had to build in a reverse method for this tree so that I could test the validity of a reversed tree. So I just reverse the tree recursively, as can be seen here. And so if I set a temp value to the left side of the node, or the left side of the tree really, but that'll be a node, set tree left equal to reverse tree right, again it's recursive, and tree right equal to reverse temp, also recursive. Then once that all the recursion is complete, I return the tree, and we're actually going to see what happens with that in a second. So that ends the node class. Then I've built in the method that we're all looking for. Now I use the Ruby use cases for this. I'm following the best Ruby practices, and instead of naming it something like is BST like we would do in Python, like this, Ruby best practices say just put a question mark behind what I'm looking for. So is BST in Ruby is written as BST question mark. And then I'm checking to make sure that this tree, the thing being passed in, is a binary search tree. Now there's one edge case that I need to pay attention to is if the tree is nil, basically there's no nodes in the tree, then it is a binary search tree technically. That just doesn't have any values in it, so it will always return true in this instance. Then once I do that, if there is actually an item in the tree, then I'm going to test both the normal traversal of a tree, so from left to right, to see if that is a valid tree. If it is, it returns true, or I'm going to reverse the tree, and if it is valid, it then also returns true, else it returns false. So again, just to build a very simple tree, just to make sure my methods worked, I created a 3-node tree. And if we actually go ahead and look at this, we can see that the node starts at root 4, which is where we start the node here. Then its left value will be set to 5, and right value will be set to 3. Now in Ruby this is a little bit weird to see. It's also kind of difficult to set up a print statement for these objects, a recursive print statement, so that it will actually print out all the nodes. But if we can follow what's going on here, I mean, if I just do a put, so you can see what it does when I put it to string, you just get the object method here. So I will do the inspect print using the P, BST, and we get this. So again, the root is 4, and then the left side is 5, and the right side is 3. Okay, so that actually just checks all the data. Now, one of my biggest worries was the reverse for this. I can actually probably call self on the BST here. No, we can't. So there we go. So again, my root is then 4, my left is 3, notice it's the opposite, and right is 5. Notice it is also the opposite. Okay, so what I've done here is I've successfully reversed the tree, and this is just to check for validity. Then I'm going to go ahead and do that validity check. So if I run the BST, or is this a binary search tree method on the BST, the binary search tree variable that I created should return back true here. And notice it does. Now if I alter this in any way, so let's say I change the order, of the leaf nodes, also get true, because all I've done is created the one node that is true, or so it can search both forwards and backwards, which was the first method that we actually looked at. And then if I don't have a binary search tree, so let's say my root node is 5, left would be 3, right should be greater than 5, and then I'll get a false reading here. So we can actually see that this is actually checking for validity. All right. So because I'm using Ruby and not Python, I had to create a new RSpec file. So I went ahead and did that. And so I require the isBST file for the RSpec. And then I'm going to describe what isBST does. So isBST, what it does is it correctly identifies example test cases. And what that means is that the original test cases that are passed in will pass with the first test case being true, the second true, the third false, and the fourth false. Now again, because I'm using Ruby, the syntax for these nodes, these objects, are a little bit different than what we're going to see in the Python file. The Python file read something like T and then 5, none, 2, etc. Instead of none, Ruby uses nil. So you can see here where I have a nil value. And in order to call or instantiate a new object, I actually have to instantiate it using the new keyword here, so node.new, and then the value of that node. So that's what I had to do to alter this from Python to Ruby, but it is in the exact same format, other than using nil for none and instantiating with the new keyword on each of those node objects. So again, I'm using the RSpec testing module here, and we can go ahead and run these tests, but let's go ahead and talk them through. So again, this first test just identifies the test cases. So my first tree has a root of 5, a left node of 2, which has a left node of 1 and a right node of 3. And then the root node has a right node of 7, whose left node is nil, and right node is 9. So again, this should be a true tree. If we were to actually look at this tree, it would be something like 5, then 2, then 1, 3, 7, and 9. So if you could imagine a line going from 5 to 2 to that node, 2 is less than 5, 1 is less than 2, and 3 is greater than 2, 7 is greater than 5, 9 is greater than 7. So you can imagine that tree as you see it, or drawn out that way. And so that would actually be a true tree. The same could be said of the second one. So if its root is 7, then its left node is 9 and right node is 2. So what we have here is a reverse tree. So 7, 9, 2. So again, 7, 9, 2. Then this is just a reverse tree, so it would be calling the reverse method on the tree itself, or on the node, the root node, and then it would check for validity. This next one is going to be returned false, so the root node is 1. The left node should be less than 1, but here it's 2, and the right node should be greater than 1, and it is, it's 3, but because this 2 is not less than 1, it's false. And so we can just traverse this one as well. So root node is 5, then the left node is 2, which works, and then the left node of the 2 is nil, so 2 is a leaf there, but the right node of 2 should be between 5 and 2, and it's 7, and so that doesn't work either because 7 is greater than 5, so it's not a BST. All right, then the next one is it handles the empty tree and returns true. Then handles a trivial tree, which is basically just a one-node tree, which should return true. It handles a two-node tree if it's in the correct order. So, well, it'll handle the two-node tree anyway, I believe, because of the reverse method. So it will check both. So a two-node tree will work. So 5 with a left node of 4 is true. If it were then reversed, so if 4 was the root and 5 was the leaf, it would still work because it's only a two-node tree. Then it does list trees, so this is where you have one extended branch. Here this one starts at 5, then the left branch is immediately 4, and the left branch of the 4 is 3, left branch of 3 is 2, left branch of 2 is 1, and so on and so forth. These should all be true because the left branches, well, fall where they should. Okay, then here you have a root node of 5, a left node of nil, right node of 4, which is the left node of nil, and this is just a reversed tree of the first one here, so it should also be true. Then the next one, root node is 5, left is 4, left is 3, left is 2, left is 1, left is 7. 7 is greater than 1, so of course that's going to be false. And then here we have another reverse tree. We notice because we have the nails in the left side, and again this is just a reverse of the previous one. All right, so all the edge cases here did turn up false. So if we were to look at these edge cases, I have a root node of 50 for the first one, whose left node is 30, whose left node is nil, and right node is 40, whose left node is 20. Now, because 40 is greater than 30, any node to the left of 40 should be also greater than 30, and the left node here of 40 is 20, so that's not going to work. And so we could essentially just keep drawing out these. So if I were to do 2, its root node is 50, its left node is nil, its right node is 30, whose left node is 40, and immediately we know that, well, we have to keep going because this could be a reverse because of the nil. So 40, whose left node is 45, which still seems to work, and whose right node is 20. Now 20 is less than 40, so it's right if we were going in the reverse node, but it's greater, or it's less than 30, which is to the left of 30 here, so that doesn't work. And again, we could just go through these, but using the test cases, we know that all 4 of the edge cases here should come up false. Then if we handle the direction tests, again, we can draw these out. So left, let me just draw this out real fast. Root node is 500. Its left node is 100. Whose left node is 50. Whose left node is nil. Whose right node is 75. And then the 100 or 500 right node is, hold on, lost my place, 75. Right node is 150 for the 100, whose left node is 125. So we're good on that side. And then the right-hand side of the 500, you have a 900. Left of 900 is 800. Left of 800 is 700. There's no right there. Right of 900 is 1,000. Left of 1,000 is nil. Right of 1,000 is 1,100. So again, if we were to follow that tree, or if you draw out that tree yourself, you'll see that all of these should be correct, which in this case, you will get a true statement. So instead of just drawing out that second branch, we're going to go ahead and just assume that because the structure is the same as all the previous nodes or trees that I've built, then when it comes up false, it should be false. So let's go ahead and run that RSpec real fast, and we should be done with this. I'll go back and make sure I comment up my node class just to make sure that it's completely understood. But let's go ahead and run the RSpec here. So RSpec on the spec folder is bst spec.rb. Notice you get all 7 examples here, and the examples are just the specific test cases, so we know that each of these works. Now, just to be sure I'm not pulling anybody's leg, I'll just change one of these to true, and we can actually see this fail out here. Expected true got false. So again, we know this is definitely a false statement here. So as you can see, each of these test cases works as they should. All right, again, if there are any questions or comments, please post them into the forum and I will answer them as soon as I possibly can. Thank you.